Friends, very good morning to everyone. Today's subject of discussion is photooxidation reaction. In this photooxidation, one of the oxidation reactions is photochemical isomerization. It is the conversion of one isomer to other isomers in the presence of the light energy. The cis-stilbene conversion to trans-stilbene is the classical example for photochemical isomerization. Cis-stilbene we have here, which we have mentioned over here. The two phenyl groups are in the same plane. That's why they are cis isomers. When it is irradiated by UV light, it absorbs the energy and it gets to converted it to trans-stilbene. The cis isomer has got converted into trans isomer. How this occurs? Let us look into it. The cis and trans isomers are the geometrical isomers. In the trans isomers, the two phenyl groups are in two different planes, and this way there is less interaction and hence they are more stable. That's why its energy is the torsion angle or the dihedral angle is found to be around is 180 degrees. In case of cis, they are in the same plane. That's why torsional angle is 0 degree. As they are in the same plane, there is more interaction. As they are having electron rich, they repel each other. That's why there is some amount of energy, that is 4.8 kilocalories per mole. How this cis gets converted into trans in the presence of the light energy? The cis isomer absorbs the light energy in the form of photons of the wavelength lambda max of 280 nanometer and gets transferred into trans isomer. Trans isomer also can get converted into cis in the presence of light energy, but it requires the wavelength of light little higher than the cis isomer, that is 300 nanometer. How this reaction occurs? Let us look into the mechanism. The cis isomer, it absorbs the photon of light and it gets excited to the higher energy level, that is S1 singlet state. It is having around 115 kilocalories per mole of energy. In this is at the higher energy level, singlet state. 70% of this will lose the energy and come down to 106 kilocalories per mole. It changes to the more relaxed, twisted S1 state. And from the twisted S1 state, it undergo internal system crossing and gets into its triplet state. In this triplet state, the order of the carbon-carbon double bond has got reduced because of its higher energy level. It is around 62 kilocalories per mole. Then in this, as the bond order has got reduced, there is free rotation. The carbon carbon bond rotation occurs and the cis gets converted into trans. And when this, it comes down to the lower energy level into the tris transformation, into the transform. 50% gets converted back into go come to the ground state of the cis form. In the similar fashion, trans isomer also absorbs the energy of the wavelength of 300 nanometer and gets excited to singlet state. Out of that, 93% get converted into lower energy twisted S1 transition state, and all this gets undergo intersystem crossing to get into triplet state. Overall, pi pi star transition triplet state occurs, and this gets converted. The free rotation is possible and gets converted into cis 50% and 50% comes back into transform. And remaining 7 out of 93% it undergoes intersystem crossing pi pi star transition to triplet state and then comes back to say cis state, or remaining 7% loses the energy directly and comes down back to trans state. Here we have seen that 70% of it gets converted into triplet transition state and that gets converted into trans. What about remaining 30%? Let us look into that. The cis-trans isomerization occurs when it absorbs the light. This goes to the higher energy level, and 30%, 70% gets converted into lower S1 state, which we have shown over here, and remaining 30% undergo electrocyclic rearrangement to 4A, 4B dihydrophenanthrin, which is represented as DHP. Singlet S1 state. This is DHP singlet S1 state. Its energy level is slightly higher than the singlet transition state of the lower energy. That's why 30% goes to DHP and 70% will be converted into lower energy S1 singlet state. This DHP loses the energy and get converted into dihydrophenanthrin, which comes down to the ground state and gives rise to dihydrophenanthrin. This dihydrophenanthrin with mild oxidizing agent like iodine or in the presence of air, dehydrogenation occurs. As we know, oxidation is removal of hydrogen or addition of oxygen. Removal of hydrogen takes place to give rise to phenanthrin. This is all about the photoisomerization reaction followed by oxidation. This is another variety of photochemical reactions which we have dealt. In the coming classes, we can look into the other aspects of photochemistry. Till then, have a nice day. Thank you.